All right, we've been talking in this chapter about two types of t that can be calculated. Shown here, this is repeated measures t right here. And I'll remind you that in repeated measures t, you can see the subscript d here. That d stands for different scores. And so when we're calculating repeated measures t, we're using the different scores. And last class period, I showed you how to calculate D, and we showed you how to calculate standard deviation using different scores, which is what you have to do for repeated measures t-test. Here's all the formulas for this repeated measures t. We also earlier in the chapter had done we had done one sample t-test as well. There's the repeated measures t. Yeah. So here was the formula for one sample t-test. And here is the example. Here's the formula for the repeated measures t. Once again, they're structurally identical, except for the repeated measures t, everything has to do with this d, these different scores. Whereas for the one sample t, it's based on raw x values instead of different scores. So last time, we had this example right here, and I calculated the repeated measures t for this data set, comparing the different scores across these two conditions, and we got 6.708. But then I also mentioned that you can calculate for a given data set like this, where it's a within subjects factor with two levels, you can also calculate a one sample t in the somewhat rare situation, though it does happen sometimes, where the sum of these two numbers, the sum of the scores for the two conditions equals a constant number, which in this case is 10. That also allows you to calculate a one sample t-test for that data set. And when we did that, we found that the one sample t gives you the exact same t as the repeated measures t. So we used two different t calculations for this one data set, but both of those t calculations gave us the exact same number, which is the way things are supposed to be, which is correct. They're supposed to give you the same number. And they also give you the same decision whether to reject or accept the null hypothesis, which requires that we use that t table, which is something I want to get a little bit of practice now. So we're going to, let's go ahead and get some practice using the t table. It's been a little bit of time since we've used it. So remembering once again that we had 10 participants or 10 different scores, our sample size was 10. We can go ahead and use the t table to find out what our critical t values are. So once again, our t value, we're going to assume that we're doing this for the repeated measures t-test, though it turns out that none of the information here would be different if we analyzed the one sample t-test, because the t values were 6.708 for both of those analyses, for both t values that we calculated. The degrees of freedom is 9. How do we get this degrees of freedom? Where did this number come from? 9? Anyone know?
N minus 1.
Yes, thank you. N minus 1. And we're going to assume that the tails are 2, which is usually, if the tails are not ever claimed or said a problem, assume 2 tails, because that's kind of the baseline. And that's just kind of the norm in psychology, is to actually use 2 tails because it's a more conservative test. But yeah, for this one, I'll just explicitly say you'll be using 2 tails. And yeah, use alpha equals 0.05. I didn't actually mention that explicitly here, but that's another thing. If no alpha is given, you assume that alpha equals 0.05. 2 tails and alpha equals 0.05 are kind of the standard in psychology. So assume those unless specified otherwise is the case. Assume 2 tails and assume alpha equals 0.05 unless specified otherwise. So now we need to go look up our critical t value. I'm telling you right here that the answer is plus or minus 2.262. That's our critical t. But let's go ahead and make sure that we can use our t table correctly. So let's go ahead and verify this by looking up the number on our t table. For you guys, in case you forgot, your T on slide 25. Your T table is located on slide number 4 in the chapter 9 slides. It's a link to the Google sheet, the Google document. Okay, so now let's go to our T table, which is right here. We said that degrees of freedom is 9. So this left column right here, this is the degrees of freedom. So our degrees of freedom is 9. And we're doing a two-tailed test with alpha equals 0.05. Here's two-tailed, alpha equals 0.05. We're going to where it intersects with degrees of freedom equals 9. And you see right here it says 2.262. So that is our critical T value, which I've shown right here, I've drawn the distribution. This is always a suggested way to approach these types of problems, is kind of to draw the distribution. And you label the critical T's kind of like this. Here's 2.262, here's negative 2.262. You can shade in the area to the left, shade in the area to the right. You'll have 2 areas to shade if you have a two-tailed test. If you only have a one-tailed test, you're only going to have 1 area to shade. It will either be on the left or the right. Not shown here is that the middle T-score would be T equals 0, which corresponds to the value of the population mean, T equals 0. And then you plot where your T, the calculated T, falls somewhere along this distribution. In this case, 6.708 is way over here, which means it is in the critical region. It's way into the critical region, actually. It's considerably into the critical region, which would mean that we would reject the null hypothesis. This is a strong effect. We would reject the null hypothesis. So going back to our data, as they're shown here, this shows that there's a strong effect such that the infants spend more time looking at the attractive face than the unattractive face, and it's strongly significant because our T is in the critical region. 6.708 is greater than our critical T of 2.262. So that's using the T table to look up a critical T value. Any questions or comments about that procedure? Okay, so I looked ahead to your homework 5, and there were some problems regarding confidence intervals. We've already done confidence intervals in chapter 8 for the Z, and things are not really that much different when you're doing confidence intervals for T. They're really the same thing. The only difference is that you're going to have different critical statistics that you're going to input into your formulas. So when I showed you the confidence interval formulas in chapter 8, it was identical to this, except this didn't say critical T, it said critical Z. And this actually didn't say S sub n, it said sigma sub n, because remember, for the T statistic, you don't know the population standard deviation, so you have to use the sample standard deviation. So this S means estimated standard error, which is basically a way of calculating the standard error where you're using the sample standard deviation instead of the population standard deviation. So these are, I guess, the 2 things that are different. Critical T instead of critical Z, and then we have S sub m, estimated standard error, instead of just regular standard error, which would have been sigma sub m. But I want to remind you that confidence intervals really aren't that much different. They're really the exact same thing mathematically as the hypothesis test, the stuff that we just did where you compare the T to the critical T. That's basically the same thing we're doing here. It's just mathematically manipulated in a slightly different way. Whereas for hypothesis testing, you assume that the population mean is the center of your distribution. When you're doing a confidence interval, the sample mean is the center of your distribution, but everything else is basically the same. I'll say that again, and I'll show you an example. When you're doing regular old hypothesis testing, like this is the figure I just showed you before, the center part is T equals 0, which T equals 0 corresponds to the population mean. The population mean is the center of the distribution when you're doing regular old hypothesis testing. But when you're doing confidence interval, the thing which is the center of your distribution is the sample mean. And basically all you do is you plug in things into this formula, and you're going to calculate a lower bound, which basically means this is like the critical region in the left tail, and the upper bound, this is the critical region in the right tail. So we're still finding critical regions when we're doing a confidence interval. The only difference is the sample mean is the center of our distribution instead of the population mean. And so I want to point out that in the textbook, it just says T here. It just says T, which I always found confusing. Even when I took this course almost 20 years ago now, I always found it confusing that they didn't say that this was a critical T. It's important to remember these numbers that you get right here, these confidence interval formulas, you get them by looking up in your T table, the critical T values given your degrees of freedom, the amount of tails, and your alpha level. Those are the three things that you need to know. And then you will look up the critical T, and that's the number that you post right here. So I'm just going to go ahead and hit two birds with one stone. Why don't you, this is, if you haven't taken a look at the homework yet, now is an opportunity for you to get it started. This problem is problem number 1 from homework number 5. So why don't you take 30 seconds here, read it. I guess I'll actually read it to you, but you can read along by yourself if you want. Okay, an all-women's college is interested in knowing whether it places more or less females in male-dominated careers like engineering, as compared to national population data for career placement. According to the National Center for Educational Statistics, only 22% of the people in engineering and physical science jobs were females in the 1990s. So this 22% right here, this is basically going to be our population mean. For this problem, assume that this population parameter, referring to the 22%, has remained constant over time. And also please note that they do not give us a population standard deviation. So they kind of give us this 22%, which represents the population mean, but also please notice that there's no population standard deviation given here, which is why we're going to have to use T. Okay, so anyway, the alumni data at this all-women's college has observed the percent of graduates placed in such occupations over the past 20 years. And so in this study, they're actually counting each year as considered like a participant. And so there's 20 years. And so they're saying this is a sample of percentages of women in certain careers over 20 years. So that's the sample size is basically 20, the percentage of women in certain careers for each year for 20 years. So it's considered a sample size N equals 20. The mean for those years is 23.7% with the standard deviation of 6.1%. So please note that this standard deviation right here, this comes from our sample. The population mean, which isn't really a mean, but the population number here is 22%. So this represents our mu. This 23.7% is our M, our sample mean. This 6.1% is coming from the sample. So we have a sample standard deviation. We do not have a population standard deviation. We have a sample standard deviation. So we want to test the hypothesis that that the percentage of women in certain careers is different than the population. So the population score was 22%. That was the amount of women in certain careers in the 90s, and then 20 years since. We want to know, is the percentage of women in these certain careers, male-dominated careers, has it changed in the 20 years since the 90s? So basically, we'll be using a t-test to compare 23.7% to 22%. Is 23.7% significantly different than 22%? Are those numbers different enough that we care? And so we're going to use a hypothesis test, assuming alpha equals 0.05. However, I want to point out that we're actually going to use the confidence interval method. So we've talked about there's the standard hypothesis test interval, which is where you make a distribution, but mu is the center of that distribution. That's kind of like the typical way of doing hypothesis test problems. But there's also the second method that gives you the exact same answer, whether to accept or reject the null hypothesis using confidence intervals, which is the main reason I'm doing this problem as a teaching example for confidence intervals. And so, yeah, the three parts of the problem, we're going to determine what the null and research hypotheses are. We're going to compute the 95% confidence interval. I want to remind you that the reason why we're doing this 95% confidence interval is because alpha equals 0.05. That means there's 5% in the tails, When you're doing a confidence interval, if there's 5% in the tails, that means that there's 95% in the middle section of your distribution. So a 95% confidence interval means 95% of the distribution is in that middle section of the distribution. We're going to make a confidence interval centered around our sample mean, 23.7. And then we will make a decision regarding whether to accept or reject the null hypothesis. So I want to point out that the way that this hypothesis is worded says, so the first question is, what are the hypotheses in formal statistical notation? Test the hypothesis that the woman's college average is different from the national average. So I want to point out that the way that this is worded, we should be using a two-tailed hypothesis test, which I've already kind of mentioned. But the reason is because the hypothesis which is stated here is that women's college average is different than the national average. It's different, which means the women's average and research hypothesis could be higher than the population average, or it could be less than the population average. That's what different means. It can mean two things. It can be either greater than or less than. And so that's this wording definitely implies a two-tailed test. So here are the null and research hypotheses. The null hypotheses, which basically means that there's no effect, that the treatment has no effect, which in this case means that if there's no effect, that basically means that the mean for those 20 years, the mean percentage of women in these certain jobs over the 20 years since the 90s, that should be the same as the population mean from the 90s. And so you would state that mathematically. The mean of the 20 years, the mean of our sample from those 20-year period is 22%. That is, the mean of our sample from those 20 years is the same as our population mean of 22%. That's the null hypothesis. Our research hypothesis is that the mean of those 20 years is different than 22%. And I want to point out once again, you can see by looking at this research hypothesis that this is a two-tailed test, because there are two conditions which could satisfy this statement. One is when the mean of the sample is greater than 22. The other is when the mean of the sample is less than 22. Any questions or comments about the null and research hypotheses for this problem? Okay, so now we need to actually calculate the confidence interval. And so I'm just going to kind of walk you through things right here. Our degrees of freedom equals 19. The reason is because our sample size was 20. And so 20 minus 1 equals 19. So our degrees of freedom are 19. We're assuming two tails with alpha equals 0.05. This is pretty standard in psychology. We need to look up our critical T. So let's go ahead and do that right now. So degrees of freedom 19, two tails, alpha equals 0.05. Okay, so let's look here. Degrees of freedom equals 19. And then alpha equals 0.05, 2.093, and it says 2.093. Good, got it right. So once again, I did that quickly. Degrees of freedom equals 19 is right there. Two tails is this bottom row, 0.05 is right there. Go to where 19 and that intersect. And right here, it says 2.093. This is our critical T for this comparison. Okay. And so when we're doing the confidence interval, remember we'll be using those formulas that I just showed you. This number right here is the critical T. This number right here is estimated standard error, which I calculated right there, and I'll explain how we got that. And then this right here is the sample mean. And then you do those calculations and you get the lower bound, which is the left, where the left critical region begins, and the upper bound, which is where the right critical region begins. So let's make sure we understand how we calculated this estimated standard error, 1.364, because as you can see, it appears right there. So you guys are going to have to know how to calculate that, for instance, for the final test. So that's 6.1. That comes from the sample standard deviation, which is right here. And then the 20 comes from the sample size, which is 20. So 6.1 sample standard deviation divided by the square root of the sample size 20, that gives you 1.364. So once again, here's our critical t's. We have a negative one and a positive one. This is like the left tail. This is the right tail. You multiply that times the estimated standard error, which we calculated right there. Same thing right here. And then you add to those, you multiply those two numbers together, and then you add to those numbers this number right here, which is the sample mean. 23.7 comes from right there. 23.7, that's the sample mean. And then you work all the calculations and you get the lower bound 20.85 and the upper bound is 26.55. And then this is something that I did mention before, though it's probably one of the more conceptually difficult aspects of confidence interval is how you make a decision whether to accept or reject the null hypothesis. And the answer is if your population mean falls inside that 95% confidence interval, then you accept the null hypothesis. If the population mean is outside of that 95% confidence interval, then you reject the null hypothesis. It's usually helpful to draw a distribution and then kind of mark, here's the critical regions, here's my population mean. Is the population mean, is it in the critical regions or is it in the middle part? So I mentioned here, I give you the answer, but I'll show you. I think I have a picture. Maybe I don't. I don't have a picture. Oh yeah, I guess it's not that. You could draw a picture, but it's also quite easy to see that the population mean of 22, that is within the confidence interval. 22 comes between 20.85 and 26.55. 22 is clearly inside this confidence interval. It falls within the confidence interval. Therefore, we accept the null hypothesis. If the population mean was not inside the interval, so for instance, if our population mean was something like 19, then we would have rejected the null hypothesis. Yep, so that's it for that problem. So this is what we just did. The hypotheses are stated in the slide. We just computed the 95% confidence interval, and we made a decision regarding the null hypothesis, and that answer was to accept the null hypothesis. Are there any questions or comments about this confidence interval problem, which I'll remind you is problem number 1 from homework 5? You will likely have to do a confidence interval problem on your final test. So this is definitely giving you practice for something you'll have to do by yourself on the test later. Okay. Got one more example here. How are we doing on time? Not bad. All right. Here's problem number 2 from homework 5 written. So let's go ahead and read this one. You can read along with me if you want. A researcher is interested in whether infants' attention to their mother's voice increases in the first week of life. Let's assume that an established baseline exists showing that infants attend to their mothers on average for 5.867 seconds on their first day. So this is kind of like the population mean. This is like the baseline data. This is the population mean basically on the first day that an infant is born. The amount of time they spend looking at their paying attention to their mom's voice, according to the study, was 5.867 seconds. That represents the population mean. The researcher selects 15 infants, so our sample size is 15, in normal health who experienced not uncomplicated deliveries. And the researcher tests the number of seconds the infant's oriented in the direction of the mother's voice on day 7 of that infant's life. So the baby is 7 days old rather. And basically the idea of this study is to compare the sample mean, which is collected on day 7, the sample mean for the amount of time that the infant spends attending to the mom's voice, do that on day 7, and compare it to the amount of time that the infant spend looking at the mom's voice on day 1. So this 5.867, this is coming from the population of infants. So this number presumably represents like the data from all infants ever. So this is the mean of time for many, many, many infants, the population of infants. Here is the sample data. So 776, there's looks like there's 15 numbers right there. This is our sample of 15. These are the amount of times that 15 different babies spent paying attention to their mom's voice on day 7 of their life. So test the hypothesis that attention to mom's voice increases over the first 7 days of life. So this is a problem where we're going to be doing a one sample t-test. The reason we have to do the t-test is because, once again, we do not know the population standard deviation. We know the population mean, 5.867, but we're not given any standard deviation at all. In fact, we have to calculate the standard deviation in this problem, which I will show you how to do. So we have the sample standard deviation, but not the population standard deviation. This is using a one sample t-test because we're comparing a single sample mean, the mean of these 15 numbers, to a population mean, which is 5.867 right here, but we do not know what the population standard deviation is. I feel obligated to point out, though, that this situation is actually contrived in the sense that there's no reason in real life where you would ever have the population mean, but you would not have the population standard deviation. So if you have the population mean, you should be able to calculate the population standard deviation. But that's, for some reason, the population standard deviation is not given in this problem. All we're given is the data from the sample. And so we're going to have to calculate the sample standard deviation, and we will be using T, one sample T. So I should also point out the first question: what are the hypotheses for this statistical notation, for this informal statistical notation? Test the hypothesis that attention to the mother's voice increases over the first 7 days of life. The way this hypothesis is worded is it's clearly a one-tailed hypothesis test because the hypothesis is directional. The hypothesis is that attention to mother's voice increases. That's a specific directional hypothesis. It's not a two-tailed test. The wording would be something like, test the hypothesis that attention to the mother's voice is different over the 7 days of life. That the test the hypothesis that attention to the mother's voice changes over the first 7 days of life. That's vague. That will be two-tailed. This is specific, a directional hypothesis. The prediction is that the attention to the mother's voice will be bigger on day 7, more time spent attending the mother's voice on day 7 than it will be on day 1. And so we have our hypotheses. Let's see if we have those here. Yep, here are our hypotheses right here. The null hypothesis is that the amount of time that the infants spend looking at is pay attention to the mother's voice on day 7. That's equal to or less than the population mean. Here's the null hypothesis right here. The research hypothesis is right here. This is where you can tell, once again, I've said this multiple times, you can look at the research hypothesis, and this is the thing that tells you whether you have a one or two-tailed test. And you can tell by looking at this, we only have the one tail. If you have does not equal, that means you have two tails. But if you just have one inequality and it's either greater than or it's less than, if you just have one inequality, then you know it's a one-tailed test. So our research hypothesis is that the amount of time the infants pay attention to their mom's voice on day 7 will be greater than the population mean. That is the amount of time the infant's been looking at or pay attention to the mom's voice on day 1. So those are the hypotheses. So now we need to draw the distribution, and we're going to draw where the critical regions are, the critical values. So yeah, in order to do this problem right here, draw the distribution with the critical values, we do need to look up the critical T value, which I've already shown you. The answer is right here, 1.761. But let's go ahead and verify that. So we're going to be doing degrees of freedom equals 14. That's because we have 15 infants. 15 minus 1 is 14. I already mentioned that this is a one-tailed test because we only have one inequality in our research hypothesis. We'll use the standard alpha equals 0.05. Let's verify that the critical T is 1.761. So let's go here. Degrees of freedom equals 14. we're one-tailed test, which means you're using the top row. Degrees of freedom equals 14. One-tailed test, so we find 0.05. Then go to where this number intersects with 14, and we do that right here. 1.761 is our critical T. And so here's the distribution that has been drawn, that I've drawn for us. And then that critical T is 1.761. And you noticed how that I've only drawn the critical T on one side of the distribution. I didn't draw it over here. Usually we'd have like a positive critical T over here and a negative critical T over here. Can someone tell me, why did I draw the critical T on only one side of the distribution? I just want to make sure we understand this. Why was the critical T drawn on only one side of the distribution?
Because it's a one-tailed test.
Yes, that is it. Thank you. It is a one-tailed test. If it's a two-tailed test, there would the distribution, there would be a critical T on the negative side as well, but there's not. So, yep, that's drawing the distribution. I've drawn mu equals 5.867. This is the population mean, which is what t equals 0 represents right here. So what we need to do is we need to calculate some t. This is our critical t, 1.761. We need to calculate some t value, and we need to determine whether that t value is in this region, in which case we'd accept the null hypothesis, or if it's in this one tail, then we would reject the null hypothesis. So let's see, what's the next part of the question here? Compute the test statistic and then show where it falls on the distribution. That's the third part. So in order to calculate the test statistic, you need to know the sample standard deviation. So this problem, you have to calculate sample standard deviation. Let me kind of move ahead, then I'll go backtrack to the standard deviation. Here's ultimately how the T formula was filled in with this problem. And you know, remember that this is the sample for one sample T test. This is M, the sample mean. This thing right here is the population mean, 5.867. You subtract those two things, that's the numerator. The denominator for the one sample T test is the estimated standard error, which the formula for that, once again, is S divided by the square root of N. In this problem, we weren't given S, we were just given this data set right here. These are the 15 scores. These are the 15 amount of times that the infants spent on day 7 paying attention to their mom's voice in seconds. And so you need to calculate, I've already shown you the answer. The estimated standard error is 0.2. And the way that was gotten was by taking the sample standard deviation, 0.7745, and then dividing it by the square root of 15, which gives you the estimated standard error right here. But I want to make sure that you know how we got this sample standard deviation right here. That is shown right here in this slide. So I haven't shown all of the work, but I've shown the way it's set up, and then I have these dots just to show that you just do this. I've shown 3 of them, but you do it 15 total times when you're calculating sample standard deviation. So we take this first number, 7, which is right here, minus the sample mean, which is 7.2. The sample mean, by the way, you calculate by adding all 15 of these things up and then dividing by 15. That equals 7.2. You take that first score, 7, minus the sample mean, 7.2, and then you square them. And you write that number down. Then you go to the next one. You have another 7. 7 minus the sample mean again, 7 minus 7.2, and then you square those things. You write that number down. Then you go to the next one. 6 minus 7.2, and then you square those two things, write it down. Then you go on to the next one. So I haven't written down the next one, but what would be the next one? Could someone tell me what would be the next thing to you kind of extrapolating this pattern? What would be the next thing that we would see right here?
8 minus 7.2 squared.
Yep, 8, which is this number right here, minus the sample mean, 7.2, in parentheses, and then you square that difference. And then you would do that 15 total times. So you go all the way down eventually. The very last one would be 6 minus 7.2 squared. Then you would eventually have 15 things. You would take the sum. You would add those 15 things together. And then you divide by 14. Where does this 14 come from?
N minus 1.
Thank you. 15 minus 1. N minus 1 would gives you 14. So you take the numerator divided by the denominator. It gives you some number. You take the square root of that number, and that gave me this right here, the standard deviation, 0.775 approximately. So that's the sample standard deviation. And once again, the estimated standard error you get by taking the sample standard deviation divided by the square root of n, which is 15. So I would point out this a difficult thing a lot of students do struggle with. When you're calculating sample standard deviation, the numerator is n minus 1. When you're calculating estimated standard error, I can say that again. I don't remember what I said, but when you're calculating sample standard deviation, the denominator, rather, is n minus 1. When you're calculating estimated standard error, the denominator is the square root of n. So sample standard deviation uses n minus 1, but when you're doing estimated standard error, you just use regular old n, square root of n to be exact. And then that calculates the estimated standard error. Then you plug all this stuff into our t equation to calculate t. 7.2 is our sample mean. That is the mean of these 15 scores right here. 5.867, this is the population mean. This is the amount of time the population of infants spends attending to their mom's voice on day 1. And then divided by this is the estimated standard error. When you work that all out, you get 6.67. So that's calculating t. Then we needed to decide, is that t in our critical region? And I want to remind you, we already have decided what our critical region is. Our critical region, our critical value for critical t value is 1.761. So we need to decide whether the t of 6.67 falls in that shaded region. And I think I have this picture right here. This person said, yeah, I should point this out. Some t tables are different, and this I actually copied and pasted this directly out of the answer sheet. And this person, Dr. Marshall, I'm presuming, used a slightly different t table, and so she had the critical t of being 1.762. We had the critical t being 1.761. There's close enough that I'm not going to count. Either one would be counted correctly. But you would see that the t value that we calculated, 6.67, is way over here in this tail. Like the critical t is 1.762. 6.67 is clearly bigger than 1.762. So we are way over here in this right tail. And so we would reject the null hypothesis. We would reject the null hypothesis, in which case we would, going back to our problem here, make a decision and communicate the results. We reject the null hypothesis, and basically what this means is, yes, infants on day 7 spend more time paying attention to their mom's voice than infants on day 1. On day 7, infants pay more attention to their mom's voice than on day 1. Any questions about this problem? All right, let's see. Yeah, so the only thing, other thing to talk about is Cohen's d in this chapter. Calculating Cohen's d really was something we did in chapter 8 when we were with z. So we calculated, remember, Cohen's d is a measure of effect size. It tells you the amount of separation of two distributions in terms of standard deviation units. It's the amount of standard deviations that separate the sample mean from the population mean. Here's the Cohen's d that we will be using for the one sample t. And I want to point out how it differs from Cohen's d for z. So chapter 8, we did Cohen's d for z. Now we're doing Cohen's d for t. It's exactly the same. The only difference is what is in the denominator. Cohen's d in the denominator in chapter 8, when we were doing z, had sigma, that is population standard deviation, in the denominator. Because for t, we don't know population standard deviation, we use S, which is sample standard deviation, when we're calculating Cohen's d. And so might be problems like this on the test, where you have to calculate Cohen's d, but these should be relatively easy because we've done this exact thing before with z. The only difference is when you're calculating Cohen's d for a one sample t-test, this is s instead of sigma. So we've calculated Cohen's d before, but we've always done it previously with sigma in the denominator, that is population standard deviation. When you're doing it for a t-test, the thing in the denominator will be the sample standard deviation. And that's all I have. That's all I have for today. So you can get out of here if you want. If you want to stick around, ask some questions, that's fine as well. Yes, I will be sending out an email regarding formal announcements regarding what I told you at the beginning of class regarding group presentations and how that'll be using the discussion forum on Blackboard. So stay tuned for that. I'll see you later. Otherwise, goodbye.